Welcome to this mini tutorial on reinforcement learning. This is essentially a minified version of the tutorial, the 3-hour-long tutorial we held yesterday, which is again based on a workshop that we created earlier. So this presentation is not going to add to anything to the tutorial we held yesterday. So if you were there yesterday, then you are of course free to go to another presentation if you'd rather do that, you know. Otherwise, welcome. In this presentation, we're going to show you the process of training an agent to play the classic game of Pac-Man using a couple of different reinforcement learning algorithms. So let's take a look at the agenda. We're going to give you a brief introduction to reinforcement learning, and then we're going to move on to our first model, which will be based on Qlearning. I'm going to explain to you how that works and then show you some code and then watch our Pac-Man in action on a couple of different maps. We're going to do the same thing using deep Qlearning, which is essentially Qlearning with neural networks. Before we begin though, let us tell you a little bit about ourselves.
So my name is Malte. I am originally from Denmark, and I'm currently working at Knowit, which is a Nordic consultancy firm. And I believe they have their headquarters here in Stockholm. I've been working there for about 2.5 years now, and I started working there right after I graduated from the Norwegian University of Science and Technology. And I did my master's in computer science with focusing on artificial intelligence. Today I'm on a project at Vy, which is the Norwegian railroad company where we price their tickets and use machine learning in production.
My name is Manu. I'm from Norway, from Oslo. For the past 7 years or so, I think me and Malte, we've been on the same path, really. We studied at the same university in Trondheim, and we also started in the same company after finishing our masters. So for the past 2 years, I've been also working at Knowit, and currently I'm outsourced to a company called Entur, which is a government-owned transportation company in Norway. And their mission is to collect all the sales and ticketing solutions for public transportation in Norway to a single application, making it possible to travel anywhere in Norway, basically using the same app, so that you don't have to use like all these different apps in all these different cities. And before working for Knowit, I was also working on my master's, and my thesis was about using machine learning, natural language processing, on tweets to predict the gender of authors. So this was based on studies indicating that men and women tend to express themselves differently in writing. There we go.
Thank you. All right, so what is reinforcement learning? So in order to understand that, I think we need to start at introducing some broader terms. So artificially is just really anything that you do to your computer to make it seem like it does something that are deemed intelligent by humans. Machine learning is a subfield of that again, which focuses on data, and that means that in machine learning, the algorithms are not explicitly programmed to solve any one problem. For instance, what a neural network learns is solely depending on the data that's fed to it, and therefore it can kind of solve any problem if you have the correct data. Now, reinforcement learning is a subfield of machine learning again, which kind of has some interesting things going for it. One of them is that it creates a data set on the fly. In regular machine learning, you usually go out, you gather some data, you do some training of the models, and then you evaluate how it works. But in reinforcement learning, you have an agent that walks around in an environment and gathers data for you while you train. It's also received tremendous hype recent years, where it's been beating the world best players in at multiple games such as Atari and Dota, StarCraft, Shogi, Go, and chess. But these games are just a stepping stone to use reinforcement learning in real life. And today researchers are looking at using it in fields such as medicine, finance, using it to control traffic lights. It's used a lot in recommendation systems and so on. So in reinforcement learning, there are kind of 5 terms you need to be familiar with, so I'm sure that everyone here speaks the same language. The first one is the agent. The agent is simply the unit that performs actions. So in the Pac-Man game, for instance, it's Pac-Man itself is the agent. The next term is action. Action is something that the agent can do. So for instance, in the Pac-Man game, Pac-Man can move to the left, up, right, and down. The third one is the environment, and that is the world through which the agent moves. It doesn't, for instance, in Pac-Man, it doesn't need to be only one map, but it can be multiple maps and all the rules that are in Pac-Man. A state is a concrete and immediate situation in which the agent finds itself and sets it in a correlation to enemies or in relation to enemies and rewards. And it's often a function of time. So you can think about it, if you just pause time, you're in a given state. And the last one is the reward. It's how we measure how the agent is doing. For instance, in Pac-Man, you would have a positive reward if he wins the game or picks up a coin, and you would have a negative reward if he gets caught by a ghost and dies. So all in all, it's going to look something like this. If we start on the left here, you have a state and a reward. This is fed to the agent, for instance, Pac-Man. And based on this state, the agent can perform an action in the environment. When he performs this action, the environment returns a state and the reward for that action, or the next state and reward for that action. And this then goes on in a loop until we reach a terminal state. And a terminal state in Pac-Man is if he either wins the game or dies to a ghost. So this is the first screenshot you guys are going to see from the Pac-Man game. It's a little bit custom made, so we can fill our needs. It's made by one of our coworkers. And the Pac-Man is the guy in the middle at the bottom, and the ghost is to the top right. And here you can see that the agent is Pac-Man, the environment is the whole game. Right now it's this map, but it could be the whole game and all the rules that are in the game, and we're in this given state. So when we want to go to the next state, the Pac-Man has to choose an action. So if we go one step, you can see that the Pac-Man didn't move at all, but the ghost moved to the left, no, to the right, I mean. The Pac-Man, that means that Pac-Man either chose to go up or down, because then the movement gets blocked and he just stays in place, while the ghost chose to move to the right. The reward here that the environment returned will probably not be anything particular, because the Pac-Man didn't even move, it didn't grab a coin, it didn't die or anything. So there's a few challenges with reinforcement learning and how it works. I'm going to talk about 3 things. The first one is escaping the local minima, because they can be stuck there, and it's about the exploration versus exploitation. The second thing is the credit assignment problem, and the third thing is reward shaping. So to explain the exploration versus exploitation, I'm going to use my puppy that I got this summer. It's a golden retriever, lovely dog, crazy, all that kind of stuff. We can think about him as an agent trying to maximize his rewards. Something you need to know before I go into this example is how my apartment complex looks like. So I live on the 3rd floor, and in order to get down, you have to go through a door at the ground floor. And when you go through this door, you can either go to the left or you can go to the right. And if you go to the left, you get out to the backyard, and if you go to the right, you get out to the street. So when he was 8 weeks old, we got him, and usually in the beginning, we would only take him to the backyard, so we always go to the left. So after a week or two, every time we opened that door, he would always run out to the left. And that is him knowing that, okay, if I run to the left, I'm going to get out in the backyard, and it's going to be super awesome, and I'm going to chew on all the sticks and dig a lot of holes. Now, the problem here is that he only goes to the left because he doesn't know what's on the right. He hasn't seen the state space that happens when you go to the right. So in order for us to show him that to the right could, or on the street, going to the right could be fun, we had to just take him there. We showed him that going to the right, like for instance going on a walk, going to meet other people, going to meet other dogs, it could be really fun too, and now he likes that. And today when we take him down, it's a little bit of a 50-50 which way he goes. And this is a problem with reinforcement learning, because if you only just take what you think is best, you're going to be stuck in a local optima because you're not going to explore the whole state space. So you have to somehow figure out a clever way to do that. The second problem I mentioned was the credit assignment problem, which is, so let's say you're training a dog and you have a treat in your hand and then you tell the dog to lay down. He lays down and you give the treat. And that's pretty simple. Then he knows that, okay, cool, every time I get down, I get a positive reward. So I'm just going to go down then. Now, let's say you don't have the treat ready in your hand and you tell him to go down. Now you have to go grab the treat, and in the meantime, he, for instance, barks. Now when he barks and you have grab your treat and then you go and feed it to the dog, then he thinks that he got the treat because he barked and not because he laid down. And this is also pretty hard for a reinforcement learning agent to understand. Sometimes you can go 100,000 time steps without getting any reward, and suddenly you win the game, and then you're like, okay, well, I have no clue what I did. Now I did 100,000 actions. Which one of them were actually good? And this has to do with what kind of rewards you're using as well. So there's two kind of rewards. There's the first kind, which is the uniform assignment scheme, also called sparse rewards. They are simply, you have two rewards. One is you get a +1 point for winning and a -1 for losing. This approach usually works in short games such as Pong, and is the optimal approach if you can afford the computations and be a little bit patient. For instance, AlphaGo Zero, when it beat the world's best players in shogi, Go, and chess, they used this assignment scheme. The agent becomes very sophisticated, but it's also really difficult to converge because of what I just mentioned earlier. The second type is called shape rewards, and here you dumb down the rewards a little bit and help guide the agent a little bit. So for instance, in a Pac-Man game, instead of just +1 point for winning and -1 point for losing, you can give like, yeah, you get some points for taking coins, you get a punishment for dying, you get a movement penalty because you want to get to the, grab all the coins as fast as possible, and so on. And this way, the agent or the training converges a lot faster, but the end result is that the agent also becomes less sophisticated because you're guiding it all the time without the agent really knowing that if it's gonna win or not. Yeah, and with that, I think you can take over.
All right. You guys can hear me all right? So are we still alive, or it's getting late, right? There are a couple of guys sleeping at the back. I can see you, but it's all right. I've done it too. But you guys got to wake up when we get to the fun Pac-Man part. Now, hopefully you now have a basic understanding about what reinforcement learning is about. So now I'm going to get into how Qlearning works. So what is Qlearning? Qlearning is an algorithm which learns Q values for state action pairs in the environment. This sounds kind of fancy, kind of abstract. What does it mean? Well, for each possible state, there are a set of actions, and for each of these actions, the algorithm will learn a Q value. And a Q value is a measure, or the quality, it's a measure for the quality of an action. It's a way of measuring success, like how happy will this action make me in the end. You can view it as an estimate of the total amount of reward that is possible to achieve by the end if you perform this specific action in this particular state right now. So when you have a fully trained Qlearning model, your agent will perform, for each state it is in, it will perform the action with the highest Q value. So Q values could look like something like this, right? So here you can see that going up, it's a bad idea, minus 1,000 Q value, that's not good. But if you go to the right, that's a positive 100. And this will hopefully become more clear with a more accurate example. So let's say that you find yourself at the Jfokus conference, and that smiley face right there, that's you in square 0. Now, how many of you guys have never been to Stockholm before? Just a couple of people? All right, cool. And let's say that is the case here, right? You've never been to Stockholm before, and let's also say that you don't have a map. So what you're going to do is you're going to just roam around these squares until you find the bar in square 8. Because it's been a long day at the conference, and you're really looking forward to having a drink at one of Stockholm's finest bars. So to be able to learn from your mistakes and also your correct decisions, we need to measure for success, namely rewards, which Malte has been talking about. So what kind of rewards do we have here? Well, if you get to the bar in square 8, you'll get 20 points. On the way, you could also end up in square 6, which is 5 points because there is a food court there and you'll be able to eat some food before you get that drink. And as we know, it's always better to drink after having some food. If you're unlucky, you could also end up in the river in square 4. That's minus 20 points, not good. We also have a move penalty of -1, and the reason for this is that you want to get to this bar as quickly as possible. You're really thirsty, so you're not really up for going sightseeing in Stockholm, so you want to get to the bar as quickly as possible, and this is kind of a motivation for doing that. And also, because practice makes perfect, you're going to try and find this bar a certain number of times, and each of these tries, they're called an episode. So when training a Qlearning model, you're training for a lot of episodes, many episodes. Squares 4 and 8, that's where an episode ends. They're called terminal states. So in the beginning of training, you will have a dictionary of Q values. We'll keep track of the Q values for each action in each state using a dictionary. And in the beginning, this dictionary is going to be empty, meaning that the Q values are all 0, reflecting the fact that you don't really know anything about the environment. Your knowledge base is basically 0. Following the execution of an action, you need to update the Q value for the action that you picked for the state you're in with the new information gained in the next state. So you perform an action in this state and then you end up in the next state, right? And this is done using a specific formula, which I'm not going to dive into right now. We're going to dumb it down a little bit. It's getting late. Don't want to bore you guys, right? So let's see what could happen if we do a test run, right? So you're in state 0, and you got 2 possible actions. You could go to state 1 or state 3, and in the beginning, you're just going to pick a random action, and you might end up in state 3, right? And now you can update the Q value for going to state 3 from state 0 with the new information gained in state 3. Here, you're just getting a move penalty, and along with the Q values in state 3, you're updating the Q value for going to state 3 from state 0 using this formula. And this goes on for many iterations. You could end up in state 6. As you can see here, the new Q value is positive, reflecting the fact that something positive happened because you got some food, right? So this goes on for many iterations. When an episode ends, you'll start over again, and then you'll continue doing this. And at some point, these values, they're going to converge. they're going to converge so that the path to that bar, it just gets clearer and clearer. And in the end, you know the best way to get there. So this is essentially what we're going to do with PacMan. What I just showed you and PacMan, they're kind of similar, even though they differ a little bit. Because in PacMan, it's a little bit more dynamic. You got several moving entities. You have the ghosts, you have the PacMan, but it's also similar because it's a grid-like system, and you can say that a state in the game is represented by how the board looks like at that moment, right? So basically, how many snacks or pellets are left on the board, where the PacMan is placed, and also where the ghosts are placed on the map. So we did our coding using Python, and we also used Google's deep learning framework called TensorFlow and Keras for the deep learning part, the deep Qlearning part. Keras is a kind of like a wrapper framework around TensorFlow, making it a little bit more user-friendly to use. All right, I think I'm going to show you a little bit of code. Not going to do much coding, but just show you and explain a little bit before showing you a couple of models. Let's see. So this is a Jupyter Notebook, which we've been using. It makes it possible to work with code and run code through a web application interface. So it's pretty neat, and you don't have to like set up a local Python environment for this. But we're actually going to run the Pac-Man game itself locally because we weren't able to connect the graphical interface to the Jupyter Notebook. So what we're starting out with in the beginning is defining what kind of rewards we're giving for each situation that can occur in the game. So what's important here is that the rewards are balanced in relation to each other so that they reflect the importance of the rewards in relation to each other. So it's all about trial and error and seeing what works when you train a model. And here are just some values that seem to work all right when we were training our model. But basically, you're giving positive values for positive events, negative values for negative events, and also when it's a very positive event, like winning the game, it's going to be a higher value than if you just pick up one of these dots or snacks. Also, the Q dictionary is initialized to be empty in the beginning. And then I'm just going to show you, I'm just going to skip ahead to the training method and explain how that works. For the number of episodes that you're training your model for, there are several steps that will repeat. So in the beginning of an episode, you will initialize the current game state to be the initial game state, right? And then in each iteration, you will pick an action given the current game state, and then the game will return the new game state and also an action event describing what happened when you made that action. So if you win the game or if you lose, then the episode is done, and then we will start a new episode when this iteration is complete. And then for each step, you will calculate the reward based on the event that happened in the game. And then you will update the Q value for the action that you picked in the state that you're in, meaning given the current game configuration, the board. You will update this using the formula that I have not explained to you, which looks something like this, but we're not going to get into that. We're just going to skip ahead to a couple of models that we've already trained and see how they work out. So I'm just going to show you the game itself quickly. So this is the game that our buddy at work created. You got the Pac-Man, you got the ghost, you got the coins, and you can move around. We also have another map set up, which we're also going to show you. So let's just see what happens if we run our trained model. So this model has not trained for that many iterations, just like 250 episodes. Each time I train it, it's like sometimes it's really good and sometimes it's really bad, and this time it's really bad. But usually it wins a couple of times. Let's see what happens now. Okay, so there it wins, right? And this map is really small. It didn't really need to train for that long before it was actually able to do something useful. We're going to skip ahead to the next map, which is a little bit bigger. Which I started out training for 100 iterations, 100 episodes. And this model takes a little bit longer to load into memory. It's a little bit bigger. The problem with Qlearning is that it's very sensitive towards the size of the state space. So a bigger PacMan map means more possible states. And over time, this is going to be very inefficient, which is why we are actually going to turn to deep Qlearning afterwards, which is less sensitive towards the size of the state space. As you can see here, this PacMan it's not really doing well at all. It's not even moving away from that starting position, which indicates that it hasn't really explored a lot of the map yet, because we only ran it for 100 episodes. So now you're probably thinking, as I was thinking, yeah, you need to train it for a larger amount of episodes, right? So I did that. I trained it for 1,000 episodes. And the problem is that this model, which was trained for 100 episodes, it was like 300 megabytes big. And when I trained it for 1,000 episodes, it turned to like 3 gigabytes, which is like impossible to load into memory. So I think we're just going I'm going to show you, emphasize this even further by skipping back to the presentation. Yeah, so it's not really able to do anything here. So the small map, the first map that I showed you, it has 12 legal positions for the Pac-Man and the Ghost. And along with the 5 coins on the map, this means that there are approximately 4,000 possible states on this map. The number is a little bit off because there are some aspects that I didn't bring into the calculation, like the fact that you have to collect some of these coins before the other coins. But it's pretty accurate. In this map, the bigger map, you've got 68 legal positions, you have 2 ghosts, and you have 53 of these snacks. This actually means that there's 2.7 times 10 to the 21st possible states on this map. It's a pretty huge number. So it's impossible to create an efficient model that can keep all of these states in memory at the same time. I think we're going to skip ahead to the deep Qlearning part, and we'll see how it performs on the bigger maps.
Thank you. Just put it in my pocket. So yeah, the simple method of just using a dictionary to keep all the states, obviously it doesn't work. So you have to do something. You're loaning a trick from the media compression world, where you're trading some accuracy for memory. The Deep Q network, they were first introduced in 2013 when they beat the Atari games at a superhuman level, and since then they just generated a lot of hype. To make our own implementation of this, we need to do 2 things. We need to scrap the dictionary and instead add a neural network. The second thing we need to do is to add something called experience replay that I'm going to explain in a minute. So now it's going to look something like this. So on the right we have the environment. Again, the environment gives the reward and a state to the agent on the left here. And the neural network then takes in the state as an input and returns 4 values, 1 value for each of the actions possible. And you can then take the highest value, which is the best action. So it takes in the state and gives out what action you should perform. Experience replay. So when you train with the dictionary approach, the regular Qlearning, you train online, it's called. This means that you choose an action, you get into a new state, and then you immediately update the Q table, right? And then you take a new action, and you get the reward, and then you update the Q table again. The experience replay is, instead of training online, we save some experiences to a memory bank, and then we can train on random samples from the memory bank. So when we're taking an action, instead of just immediately train the neural network on that single action and reward, we instead save it to a memory bank, and then we can do a lot of actions, and then we can batch them up, and then we can sample random samples from the memory bank. There are two main things with this that is really nice. First one is that the DQ network, it usually forgets early runs if you don't do this. So let's say you're at the level 2, the big map, and the PacMan starts to learn a little bit the start of the map. But when it starts to branch out to the sides, if you do online training, it's going to forget how to do the first part. But if you instead save all the experiences to the memory, it's going to take random samples from the memory bank, meaning it's going to train a little bit on the later part, a little bit on the earlier part. So it's not going to forget any early runs. The second advantage is that your neural networks usually needs a lot of data. And it's just good to save this experience to a memory bank so you can train it multiple times. And because when you train a neural network, the updates of the weights are very small increments. So you need to train on the same experiences multiple times. Yes, that's experience replay. Now, when you introduce a neural network, we need to make another change to our program. Because neural networks, they take numbers as input. So for now, we have used a string representation of the state as the key in the dictionary. But now we need to somehow map the state to just one long vector. And we're going to do that using one-hot encoding. How many of you guys know what one-hot encoding is? Okay, so only a few. I'm going to try to explain it then. So one-hot encoding is usually used for categorical values, where you make one vector for each category. And the length of this vector is the same as the number of categories you have. So in this code bit here, you can, I think you can see it pretty well. We have 5 different categories, right? We have the O, which are the fruits in PacMan. We have the space, which is just nothing. We have the P, which is the PacMan. We have G, which is the ghost. And then we have the dot, which is the dot or fruit or snack or what you want to call it. You make a vector for these. In each vector, they're all zeros except for one of the numbers, and these are then identified as this category. So it's going to look something like this. At the bottom left here, you have the string representation of the level 0 map. Then you start at the top left corner, and you just loop through it. And you concatenate these vectors into each other. And what you're going to end up with is one long vector that represents only that state. So if you, for instance, move PacMan 1 to the left, the vector is going to change slightly, and the neural network is going to know that. This long vector you then use as input to the neural network, and the neural network is going to feed you back with 4 values, which is 1 value for each action. It goes left, up, right, down. So when you want to choose the optimal action, you simply just choose the largest number here. So let's look at some deep Qlearning on PacMan. Let's see, I can maybe show you some code first. We have about 10 minutes. Should be fine. So here again we have the same, a lot of the code are the same, so I'm just going to show you the most important things. Yeah, you guys can see. So here we have the rewards again. And as Manu said, the relationship between the size of the rewards are very important. What's also important when you have neural networks is that these rewards don't get too big. For instance, if you just time all of these or multiply all of these rewards with 1,000, they're still going to have the same relationship, but they're going to be really large numbers, which the neural network doesn't really like because their weights are small and the updates are very done in very small increments. So these values for the rewards worked for us a little bit. Another problem with these shaped rewards, right? These are not the uniform assignment scheme. These are the shaped rewards. Is to actually make these rewards, because why should I tell the Pac-Man how good it is to grab a coin and how bad it is to be captured by a ghost? I kind of want the Pac-Man to tell me how bad it is to be taken by a ghost and how good it is to get a dot, which then you have to use the uniform assignment scheme. And then it's harder to convert, so we have not done that. Here you have the convert state to input. The neural network itself is right here. We're using Keras. It is you have the input layer, which is the same as the size of the vector that you get from the state. You have two hidden layers with the size 256 and one size 128, and then you have the output layer, which is the size of the number of actions, so 4 in this case. Yes. And here you have the exploration probability. The one way of combating the exploration versus exploitation problem is to simply, at each time step, you have a small probability of the agent doing something random. So for instance, when my puppy would always want to run to the left, at some point, he's gonna try to run to the right, and then he will explore that state space as well. You have the implementation of experience and memory. And I think that's about it. So let's look at some PacMan using this. We're going to start with the level 2. So this model is trained for about 26 hours on my GPU at home, which is a GTX 1080 Ti. I did 5,000 episodes. That means that the Pac-Man played 5,000 games, and we're going to start looking at how it performed when it only had run for or trained for 500 episodes. Let's see. Yeah, so now it's been training for 500 episodes right here. An interesting thing you can see is that it runs straight to the mushrooms. The mushrooms in Pac-Man make the ghosts scared so that they can't capture Pac-Man and they're just going to run around. And I don't know if the Pac-Man itself had thought out that, oh, if I just take all the mushrooms, then the ghosts are almost going to be scared all the time. Or that I just made a poor choices for my rewards and said that, well, when you take a mushroom, it's a lot of points, so that's why he just immediately runs to them. It's hard to tell. So he gets pretty far after only training for 500 episodes, but he struggles a little bit at the end. I think he definitely overperformed that one. He usually dies way earlier. One other thing to note is that in our version of the game, you have 3 lives, so you can be captured by the ghost 3 times before you die. So if you die the first and the second time you die, you're just teleported to the starting position. So let's look at how he performs when you train for 2,500 episodes. And again, he does the same because he learned very early on that the mushrooms are awesome. And eat mushrooms. No. They're healthy if you buy them from the store. Yeah, so we learned that very early on. Here, when the ghosts were scared, if you Pac-Man then captures the ghost then gets teleported back to their starting position. And is he actually gonna win? I think he's gonna win. Wow, that's a good day for deep Qlearning and a bad day for Qlearning. That's good, that's cool, that's cool. All right, so let's see almost at the end of training how he performs. And again, he runs for all the mushrooms. A little bit of an issue with this map is that, oh, he actually died there. That is not usual. Is that I think there are too many mushrooms, because when you just run to all the mushrooms, the ghosts are usually just scared for almost the entire duration of Pac-Man trying to solve this map. And now he's performing really poorly when you train for 4,500 episodes. So maybe it's not a good day for Qlearning after all, or deep Qlearning after all. Oof, actually lost. Okay, I have to play it one more time then. Oh, like come on. I think that might actually be the first time I've ever seen him lose at 4,500 episodes. So sometimes an interesting happens here. When he gets this far, you can see that he is taking all the coins on the left side and only coins on the right side or left. Sometimes he has the choice to either avoid a ghost and run like in a long way around like all the obstacles to get the rest of the coins, but sometimes he has learned that if he just suicides for the first life, he'll get teleported to the middle, which means less running for him, and then he can run to the other side. So that's pretty cool. He does that sometimes. Here he died. I don't know if it was on purpose or not, but sometimes it's actually pretty clear. We have a little bit more time, so I can show you guys some more levels. So I did this. This was 26 hours of training time. And when I saw this, I said, okay, well, he managed to beat this. Well, not 100% of the time anymore. I guess it's 99 now. But I thought, okay, well, there's too many mushrooms on this map. It's too easy for him. So I made a different map. It's a little bit bigger again, so the state space is even bigger. And this is, yeah, one mistake I made when I trained the other map was that I only saved the model after every 500 episodes, which was kind of stupid. So I started saving them every 100 episodes, so you could maybe see more gradually how it performs. So this is after 100 episodes on a new map. There are 2 ghosts here, and there are only 4 mushrooms, and there's not that many obstacles. So there, he dies pretty fast. This is only after 100. So let's see after 1,000. This one I actually only trained for 1,000 in total, because I was watching the training, and he did not win a single game before 1,000 episodes, so I just quit the training. I was too disappointed in him. But I also think that this map is pretty hard, at least if the ghosts are a little bit competent, because they can literally just push him into a corner and kill him, right? But after 1,000 episodes, sometimes he gets pretty close to solving it. And when he gets up into that top right corner, he ain't leaving. Yeah, let's see, 5 more minutes. Okay, so so I saw that one, and I saw, okay, 2 Pac-Mans, that's way too hard. So I made one with only 1 Pac-Man, and I got only 1 ghost, yes. So there was 2 ghosts on that one, and so I made one with only 1 ghost. And I'm thinking, okay, this one is going to be easy. So this is after 100 episodes again. And it performs about the same as the 100 episodes on the map with the 2 ghosts. Actually doing a little bit better now. It's managed. Again, this is when I really realized that he only runs for the mushrooms. And I think it's because I gave the mushrooms too high of a reward. I think it's that simple. I think he just gets a lot of points for the mushrooms, and he's like, okay, I'm going to take all the mushrooms every time then. Because he's not doing so well right now. Yeah, we'll see if the ghost can catch him eventually. There you go. So this one I had higher hopes for. I also monitored the training, and after 1,000 games he did not win a single game, but this time I was not going to give up. So I trained it for a total of 4,000 episodes. Still did not win a single game, spoiler, but sometimes he gets pretty close. He always just immediately runs for the mushrooms. This is something that I've seen. When they've trained for enough time, they just immediately run for the mushroom. And then he gets pretty close. I've seen there being around 3 to 5 coins left. I don't think this is going to be one of those times. Run to the left. Come on. Yeah. Oof. Oh well. Yeah, so that was how the deep Qlearning. I think that, we can go back. I have 2 more minutes. We can just... Yeah, so improvements. There are 5 improvements that you can do. The first one is we had a flat 0.2 exploration rate, right? So 20% chance that he's just going to do a random action. But usually what you want to do is that this factor is high in the beginning, right? Because you want to explore in the beginning, and then when he starts to figure out strategies, you want the exploration rate to go down, so he just exploits all the time. Another thing you could do is to use convolutional layers. This neural network is vanilla feed-forward neural network, and convolutional layers are really good with 2D inputs, so they're often used on images and stuff. But the PacMan map is also 2D, so it could be interesting to see if that performs, or increases the performance. The obvious one, more training time, more memory, more processing power. I think that the PacMan definitely would beat the last one with only 1 ghost. If you just trained it for longer, at that point it was probably up in 40 hours, and I wanted to use my computer, so no more training for that one. And it didn't win a single time, so I got demotivated. But if you just throw more at this, I believe that it's definitely going to work, at least on the last map. You could also add a new neural network which stabilizes training a little bit. And then lastly, you can use prioritized experience replay sampling. Instead of just sampling randomly from it, you can prioritize, so you can see that, okay, the Pac-Man doesn't know what to do when he gets on the left side of the map, so you can gather experiences from the left side of the map. Yeah. And with that, I'll say thank you for coming. And the slides here are on our Twitter, so if you guys want them, you can go on our Twitter. Thank you.
repository.
Okay. It's the link to the repository, not the slides. So if you want to play around with the PacMan, you can go to our Twitter.